All right, in case anyone has forgotten, we have a midterm coming up. I have posted on Piazza these locations, but I cannot post them on the website because of different security stuff I can't talk about due to an incident that happened a while ago. I will do a minor content warning for today. I will briefly be I will not briefly, I will in depth be talking about what happened in Syria in 2012. Syria shut off the internet, and whenever I talk about these sorts of things, one, I try to warn you in case there is anyone in this room that was impacted directly. I also focus almost exclusively on what happened technically. So we will not be talking about what actually was occurring in Syria. We're talking about specifically what's happening from a networking perspective. But that will happen after the first share, think, pair, share. So if you need to leave the room for any reason, you can. All right, we made it this far last lecture. Last lecture really wasn't about security, let's be blunt. It was just a pile of networking concepts so that we could even start discussing security. Today, we're going to slowly start discussing security, and then after the midterm on the Monday, we will start actually talking about real security in networking. It just takes so much knowledge to hit the point of even being able to discuss real security concepts. But I want to, okay, that was slightly out of order, but when we talk about security and networking, we're almost always talking about availability. Networking makes no effort at confidentiality. None. You give it a packet, it will convert it, take it across. The biggest thing networking has done recently at all around this is shift from hubs to routers. It used to be the case that a packet came in and it just sent it to every computer. Now it has a little think and only sends it to the computer that needs it. But in my personal opinion, they did not do that for security reasons. They did that for congestion reasons. Networking people care about availability. They care about getting that packet from point A to point B. This is their primary control. And they care about throughput. How much data can I get through? How fast can I get it through? And how do I lose the least number of packets? And they have no problem with losing packets. Their only problem is losing the least number, and if you want it, telling you that you lost them. We focused on TCP. There's also something called UDP. UDP makes no guarantees. It's like dropping a postcard in the mail. Like nothing will come back. So networking focuses entirely on availability. They also have no care about integrity. There is no checks anywhere in the lower levels of the OSI stack anyway, on whether or not the content was fiddled with. In fact, they fiddle with the content all the time. Availability. I'm going to introduce two threat models. We might touch on them a little bit off and on today, but we'll be talking about them a lot more in the next one. Okay, we're always concerned about this man-in-the-middle attack, but I described that as like this big fuzzy group. Let's talk about more specific two groups. One of them is insecure developers. We'll just call them vibe coders for this moment. So I want you to imagine someone has decided they're going to make a new widget. They have a soldering iron, they have some components, they solder these things together, they now have a smart tea kettle, and they vibe code the stuff for it. Security must have been included in this whole AI thing, right? And then that person happily goes and sells this to millions of people who then plug it into their home. Now, you are not thinking of this person as an attacker because they are not trying to attack. This is not someone is intentionally attacking anyone, but they are almost an enabler. They're creating vulnerabilities all over the place, which then might be used by someone else. Think about the news article we talked about, right? People were very genuinely trying to allow apps to make web pages. Maybe an app needs to make a web page. But an attacker will try to chain these things together. So this is one enabler, I guess, rather than a specific attacker. The other one is data aggregators. So data aggregators usually sit just barely on the legal side of the law, predominantly US law. And they will just try to collect as much data about you as possible and sell it. Bluntly speaking, this is what they do. They collect data and they sell it. Every time the US government comes down and says, law enforcement, you cannot collect data on Americans, And law enforcement says, well, yes, we will not collect data on Americans. We'll just buy it. And I have a lot to say about data aggregators. This group is trying to view. They are very rarely trying to attack directly because they don't want to attack you. They want you're producing mountains of data for them. That data has value, and they would like to sell it. And so they are just continuously trying to collect as much. You would never know if they're looking because they're silent. But it can have some very real consequences. These are bought by insurance companies. They are bought by lending companies. They impact the sorts of ads you see. ICE agents in the United States, and I'm very sorry to say this right now, are using this data. And I would not even call this accurate data. So this is a threat. All right. We're not doing Think, Pair, Share right now, but I'm going to drop a question on you. And then we'll come back to this in 2 sections. So this is I had ChatGPT or Copilot just generate me a random image of a smart thermometer. So this isn't even necessarily a Nest. But imagine you had a smart thermometer. And if you read the advertisements to these things, they're like, oh, it's so great to have one of these things. It will reset your temperature or do all this awesome stuff. And if you're away from your vacation home and there's suddenly an ice storm, you can bump the temperature up or remotely check the temperature in your house. Okay, 2 questions off this. One, you're about to learn how we block access from anywhere. Do you really, think about this for a moment, do you really want a random web server out on the internet able to reach into your home and access random devices? Keep in mind the threat model I just mentioned. No, you really don't. So there is actually technology that blocks this. And then how do you think they're getting around it anyway? All right. Just starting you thinking on this. We were supposed to get to ports last time, so we're still basically not on a security topic. We're still on basic networking. But let's go through ports, and then we'll start moving into some of the other stuff. Last time, I talked a lot about things like IP addresses, MAC addresses, OSI network model, right? So this idea that I'm trying to get data from computer A to computer B. But what is data anyway? Data is usually a whole pile of ones and zeros. If you have ever tried to open an image with a text editor and regretted it, you will know that any application can really try to open any file. It's just a pile of ones and zeros. It depends on how you are interpreting it. If you try to ask Word to open something that maybe has weird characters in it that a different program would have handled just fine, you will see a different rendering because it's just the ones and zeros. So it really matters that when that packet comes in, we know what to do with it. We know that these ones and zeros are gzip, for example, which might radically change how we interpret them. Now, network engineers date back a long time. They date back to when we don't have very many bits and bytes to work with. We're very rich now in terms of data. They made those headers as thin as they can make them. And they do not want to be inserting extensive instructions on how to interpret this packet into every single packet because they care a lot about speed and throughput and availability. So what they decided to do was build something called a port. I say build, this isn't overly exaggerated. A port is a number. They created a little section in the header called port, which is simply a number. And that number is set up to link to a program within an application or within a computer. So each computer will have a set of what it calls open ports. So each service on the computer, everything that's actively wanting to talk to the internet will be listening on a port. Listening on a port just means that there's a little file inside the computer that lists this port, this application, this port, this application. If a network information comes in, it is then routed. It looks it up against the port number. It says, that port, and then sends it to that application. If a packet comes in and it lists a port that nothing's listening to, it gets dropped on the floor. And this is what we call a closed port. Closed and open just mean, is there anything listed in this table against that port number? Yes, no. If there is, we forward it. If not, we drop it.
So if I try to open the connection against the closed port, will a file descriptor be created?
No, nothing will be created. If you try to access a closed port, it's literally dropped on the floor. The things like, I'm not listening to you. If you're trying to access a service that I am not advertising, no.
So the file descriptor has to be created by something, by service.
File descriptor.
Yes.
No, we never hit file descriptor.
But a port is file descriptor, isn't it?
Okay, I'm not getting that deep.
Okay, fine.
At this point, we're mostly thinking of a port as an element in the header. So if you think of this from the OSI network model, a bunch of bits and bytes come in across the wire. Those are then interpreted as we go up. Once we've maybe put a whole bunch of those bits and bytes together into a message, we might say, okay, well, is this port being managed? This gets a bit complicated because a lot of computers are running firewalls, and the firewalls may drop port info based on the ports coming in on the packets. They may drop the packets before we ever reassemble them. But if we think of this from a theoretical perspective from the OSI model, then they might come up to the point of, say, the transport layer. The transport layer may go, okay, what port am I supposed to send this collection of packets to? And then it goes, I don't have a port to send it to, drop on floor. And do not further process. This is a strict security decision because you have two problems. One, if you don't know what these bits and bytes are, how are you going to process them anyway? And two, a lot of attackers like to send random garbage at people's computers constantly. And so if you're not expecting something, don't talk to strangers. All right, in this picture here, I have this little diagram. It's not very complicated, but imagine you have a client application with web server, and then you have a web server. And what's happening is this is, okay, I'll come back to why this is a port, but they have different ports that they're listening on. The client has ports and the server has ports. And I will now step into that. There's, broadly speaking, two types of ports. They're kind of named ports. Here's a whole bunch of examples of these. This is a convention and not a protocol. This means that these are the ports that are the defaults. Like if you set up a new web server, it will probably register itself against port 80 and port 443. It will just do that by default. That said, it will have a config file, and you can happily go shift it to port 22 if you feel like it. So these are the ports. These are the low-numbered ports. I forget where they go up to. I know it's below 3K. Above 3K, roughly, are the kind of unaffiliated ports. The computer can have as many of these as it feels like, and it just uses them for whatever. All ports, it's entirely up to the local computer how they are used. Okay, but the thing is, when I have a communication with something else, it needs to be two-directional. Because my browser isn't just sending data at the server. It would really like the server to send a web page back. So the server is intentionally trying to serve things. It has a web server launched. It has a service. It wants to talk to strangers. It's like, talk to me. I'm on this IP address. Your computer doesn't want to talk to strangers. So it doesn't have any open ports. If you do a port scan of your own laptops, I mean, I realize this group maybe not, but most of you should come back with nothing. Because you should have no open ports normally. So what happens is that when this client tries to talk to the web server, the computer automatically opens a high-numbered port. Usually when it's done as part of a TCP connection, that port is then hooked to a specific IP address or a specific destination it expects it to come back from. So it's doing a little bit of security access control there. But it now just basically opens that port. Now you can have a communication back and forth because what's happening is the client sends things out across this port. It goes to the port 80 port on the server. The server goes and constructs the web page, sends it back across the connection with a destination of the client port. All right, are we kind of still all okay? This is basically a big mapping just to make sure the right application gets it. So when we talk about networking, networking does not end at the networking card. It also includes how things are interpreted on the computer to some degree. All right, tell me if this makes sense because we're about to go a lot deeper. natty. This is one of those things that's unintentionally security oriented. This is done for a completely different reason, but it has security implications. All right, so this is my IP address when I took the screenshot when I was connected to Waterloo Wi-Fi. So you can see down here that I have an IPv4 address of 10.32.15.86. This is from several years ago, so no, you can't ping that. But when I go on the internet and I type, what's my IP address? It says that my IP address is 129.97.124.26. That's a different IP address. Why are they different? Well, we learned last time that IP addresses need to be unique on a network, and we can kind of consider the internet, or at least the internet, the connections between the different networks to be one network, where it needs to have isolated IP addresses. What's basically happening is we have this problem. When people invented the internet, they were sitting there going, well, there aren't that many computers that could even support this. So we'll make an astronomically huge number of addresses in the billions, and then we'll almost never use them all. And this is not how the world went. There are far more devices out there than we have available IPv4 addresses. This is one of the reasons we're trying to shift to IPv6. This means, though, that it's not possible for every computer on an internal network to have a globally, like the planet-wide globally unique address, because we'll have clashes. And so it is necessary actually to conserve our IP addresses. This information is data, but if I remember correctly, China, like the whole country at one point, had less IP address range than Carnegie Mellon University, where some of this was initially invented, because they had access to a lot of IP addresses. You have weird problems out on the internet. So our solution to this is what we call network address translation, NATS. Network address translation means that I have one address when I'm inside and then the internet sees a different address. That means that most of this room, if it were to ask what is my IP address on a website, may actually come up with the same IP address, because we're all sitting behind the university's IP address. All right, I have a lot of animations of this. So, guys, keep in mind, we're also still dealing with ports. So imagine that I have this home PC over here, and I have this destination PC over there. And just to be extra confusing, they both have the same IP address. They can do that, they're on different networks. And I want to send between them. If I try to send this from my home PC over here, sorry, I have to turn this direction or the mouse doesn't work. And I say, please send a packet to 192.168.4.2, what's going to happen? It's going to loop straight back to me. And it is not going to go to that web server over there. And that web server wants to be seen, right? They have a publicly open port. But how? Because they're sitting behind this router. They're in their own little network. There's no way on earth they could be advertising their IP address and have a port. Hence natting. You notice that each of these routers are producing effectively a bridge. They're connecting two networks. So like the router sitting up in the corner of this room is not connecting two networks. It is disconnecting you to the rest of our internal network. But there's border gateway routers, and they connect the inside of one network to another network. Most commonly the internet, but it could be really any network if we really wanted to. And as a side effect, it has at least two IP addresses. It's got the internal IP address, and then it's got the external IP address. And in order to do this, it has to edit all messages going across. So what's going to happen, this is me just screenshotting my laptop when I had VirtualBox running. So what's happening here is that my laptop actually is bridging 3 networks, or 2. Your laptop can bridge a surprising number of networks. If you just hit the button that says mobile network, like be a hotspot button, your computer will do the exact same thing as this router. What it's doing is it's just saying, oh, I'm going to offer internet You come in, and then I will move it across my own stream and drop it on a different network. You basically created 2 networks with a mobile hotspot. The ones that are connected to you, and then the ones that are connected in other places. This is just all the different, these are all the different Ethernet systems that my computer theoretically has access to. All right, so we start with a message. Our message here is for 173.162.146.61, and it's going over port 80. Port 80 is the unencrypted network port that's most commonly used for web pages. I pick it because it is shorter than 443. This address is the address of the border gateway router over here. Because if we want to reach this computer, actually, we need to reach this computer over here. Actually, we need to access the router. When things are advertised across the internet, and we haven't really talked about advertisement, but if you type in, say, facebook.com, it will resolve to this router's address and not to an internal web. And so you would know what this is. And then we're sending it to port 80. So that message moves across to my local router. My local router edits it. It drops its own external IP address on it, and it gives me a port. So I'm going to go back a moment. That home PC is using port 5338, and it suddenly changed to port 7648. What has happened is if that home network router gets a whole bunch of packets in, how does it know which computer to send them to? On the inside. It doesn't. There's nothing, I mean, that we don't know the interior of the next network. And so what's happening is similar to how on a computer you use a port to indicate what application. The router is dynamically creating ports to remind itself what the internal computer link is. So port 47648 has now been noted down in the router's internal systems, and it said that actually maps to this address and that port. And you'll see that in a moment when I roll this backwards. So it rewrites both of those. It then goes across the internet and lands on this router for this network. This router for this network then furthers edits. It goes, if you're looking for port 80 is mapped to this computer. Some of you who think about building websites may suddenly go, wait, you can only mount port 80 to one computer. And the answer is sort of yes. Yes, from a networking perspective, you can only map port 80 to one computer, but it's possible that computer then takes it and load balances it onto others. All right, so we then remap it. We put in this IP address. That router has done the same thing. It said port 80. Okay, which computer does port 80? It's this one. It does the remapping. It now heads up and goes to its destination. Now the destination happily puts together whatever web page has been requested, and it creates a response message. This response message is destined for 192.41.131.255. It's destined for this router, right? It's not listed against this computer. It's listed against the router, and it's using the port number that this router created. It comes down and hits the router. The router goes, nope, you're not 192.168.4.2. You have to use my IP address, so it converts the IP address. It does not change the port, though, because this has been port 80 the whole time. It then sends it across the internet to the home router. The home router then further modifies it. It puts back on the original IP address and the original port. And then it goes to the home PC. The home PC, because it opened this port for presumably Firefox, now accepts something coming in at this port as going to Firefox, and the web page loads. All right, is everyone still with me? You look confused. Okay.
Can you try again? I zoned out.
All right, this is why I'm recording. We're going to move to think, pair, share, and then you can think a bit more about it, and we can figure out if we have some. So our question here, I've been talking about this from the perspective of laptops, but our thermostat doesn't look any different from a laptop. It's sitting inside the home, right? Home network. Maybe it's this personal device, maybe it's something else. It's just one of the many computers that's connected to this router. And the network does not differentiate. It's just, this is another device. Why can't anyone just access it from anywhere? So how come you can't, while you're happily out shopping, just send a message to this thermostat? And how might you fix that as an engineer? Because clearly you can send a message to this thermostat. It's on all the advertising. But why couldn't you just natively do it? What do you have to kind of get around, and how might you get around that? All right, think better, share. 1 minute of silence. All right, we're going to now go through a massive change of topic. We were just now talking about this on a very detailed scale. So inside of a computer, sending messages. We're about to shoot up into the clouds. Because up till now, you've been talking about internet as if it's this big fluffy cloud, and you put some data in one end and somehow it comes out the other. How do you do that? Part of the answer is something called autonomous systems. And this is how psychology, economics, business all crash into networking. So the internet is owned by a lot of different groups. So long ago, when it was ARPANET, it was effectively owned by some mix of the universities and the military. When it was opened up, it wasn't owned by anybody. But how on earth, if something's not owned by anybody, do you manage it?
Yeah.
Your other problem is, how can I put this? System administrators, particularly system administrators in the 80s, had a strong view of don't touch my network. I want to run this as a token ring, and no, you don't have the right to tell me not to run it as a token ring, and no, you don't have the right to tell me to use TCP. They were very territorial, let's just put it that way. So the original system was designed to dictate how people run networking between networks and leave it open on how they manage it within networks. So the internet is called that partially because it is an interconnected network of networks. And there is no rule saying that an internal privately managed network has to use any particular thing. If this university tomorrow wanted to launch a new networking protocol within the university, I think it would be a total nightmare. But the global internet would not care. And it's designed that way. This is why you hear me using a lot of words like border network router, border. These things have borders. I showed you this picture a while ago. This is just kind of trying to highlight the same thing. You have these big, what we call autonomous systems. They're little clouds. They're little networks, or they're not little, sorry. They're massive networks, and they have borders around them, and they interconnect with each other, and they interconnect with their clients. So you'll have a Verizon network here, for example, that might go to British Telecom and have a big pipe to British Telecom. And then it may also interact with a whole bunch of individual clients that it's, or paying clients that get network traffic. And this is how traffic flows, right? Because it starts down at one of these computers, goes under Verizon, British Telecom, level 3, and ends up over at a server. It's traversing them. Each of these networks has a network inside of it, of the discretion of the admin. Time has moved on, and admins, like most people, are slightly lazy, and as a side effect, they no longer really try to enforce weird things, and most of them are running TCP internally within their network. And so a lot of these smaller networks do look like the larger internet at this stage, but again, not guaranteed. And each of them has, up till now, I've been kind of just talking about this one network router. There is not. There is a set. So here's one, here's one. There's a whole bunch of different connections. And when we talked about this very early on, I was like, okay, there's a wire. There's a hop between this computer and that computer. At the end of the day, you have a connection medium, which may be a wire, it may be a satellite link, it may be something else, but there's a computer-to-computer link. And these border network routers, they speak to other computers across these narrow links. There are a lot of them. This is from 2020. I looked it up yesterday, and they do not have a new version. Each of the dots in here, which you can barely see, are autonomous systems. The ones in the middle are the highly connected ones. The ones on the outside are minimally connected ones. I'll come back to that in a moment. Let's see. These form little pyramids. This is where economics is now starting to crash into the side of networking. It costs some money to run a router. But do you guys pay the main ASs in the middle of the network? No, you pay your internet service provider. So your internet service provider then pays a network that's further in, which then may pay another one. And this results in these little cone triangle things. Customer cones, customer chains. So in autonomous systems, A, E, and F are the ones kind of on the outside of this graphic. And then they are all sending data up to A. A is then one of those backbone autonomous systems, which might send it across into a completely different cone, like G, and then send traffic down. You can route a bunch of these through different routes, but at the end of the day, when you want to do something like cross an ocean, there's only so many ways to do it. And so a lot of these are not peer routed. You'll have like a small, like say Rogers Internet, which I know it does not think itself as small, but is much smaller than say Verizon. And will, as a side effect, collaborate with Verizon in order to say cross the Atlantic Ocean with your traffic. These form whole cones. When I say customers here, I do not mean individuals. I mean other ASs. So these can be incredibly large and contract with a lot of them. Keep in mind there are many very small ISPs, for example, that have an AS status, but may actually only cover a very small community. And so this is why there's just so many and why these cones can be so big. This is just a short version, again, on why we're talking about IPv4, and I've just kind of not lecturing IPv6. This is what it looks like for IPv6 in 2020. This is what it looks like for IPv4 on the left. We're still not seeing IPv6 adoption at the levels we would like. It's really hard to change how people use the internet. Traffic can take really weird routes across the planet. You might think crossing an ocean is expensive, and maybe we shouldn't be crossing the ocean 2 or 3 times to send network traffic. You might be wrong. Because when I talk about network distance, I do not mean as the crow flies. I do not mean how long the wire is. I mean how much money this AS associates with that connection. And so they will weight connections based on things like agreements. So maybe Verizon and T-Mobile have an agreement saying that they will share a certain amount of traffic without cost. So what will happen is that it will weight routes to prefer going across that cost-free connection up to a certain threshold, and then it might reweight things to go across another one. So when we talk about costs here, we actually mean money. And this causes weird routings. This is me. I think this is me. Yeah, no, you can see here at the top. I'm at University of Waterloo, and I'm trying to gain access to Vanier.com, which is down here at near the bottom. You can run a program called Traceroute. I'm not going to get to the details of how Traceroute works, but you can pull up a web page that will run this for you, even if you would like. It just tells you, gotta be very careful here. It tells you with okay accuracy what route your traffic is taking. It does not tell you with high accuracy, so it's a fun thing to do, but please don't base anything serious on it. It can be wrong. This is a tracebook from the University of Edinburgh, so Edinburgh's in Scotland over there. Why on earth is it sending traffic halfway across Canada, halfway back into the United States, and then across? This is a trace route to QQ, which is located in China. One might think that, oh, it'd make sense to, say, just send it across somewhere, but I know it decides to hop through a phenomenal number of US locations, cross the network for some reason into Scotland, and I don't know why it's crossed into Scotland, and then end up in China for QQ. If you try this yourself, you'll just get a ton of crazy routes. This is because it is reducing weight economically. Or because some network engineer wants that route to be shorter for some reason. I'm coming back. I've heard this from this class before. Why do I need to verify CAs? Why am I worrying about certificates and making sure I'm talking to the right thing? If I type Google in, Google always shows up in my web browser. Okay, but how did I find Google? I mean, I'm picking on QQ mostly because it's in China, but QQ is a big service in China. It is not a small thing. If I type QQ in, I would expect QQ to come back up. But the decision on whether or not the actual QQ web page comes up is a decision held by every dot on this map. Every single dot on this map has the ability to be a man-in-the-middle attack. And the only thing stopping it is the fact that you can actually verify this really is QQ using certificate authorities. This does happen, by the way. I don't think I have a really good example for here, but this is not the case. So if I'm an attacker and I'm not sitting on the connection between the two people I want to listen to, how about I just move the connections? The example here on the screen is not well, it is. This is mostly funny. There was an artist located in, I think, the United Kingdom, and he said to himself, could I cause a whole bunch of cars to stop going over a bridge? So what he did is he took 99 cell phones, put them in a wagon. This is a picture of him hauling this wagon over this empty bridge. This is a screenshot of the bridge from Google Maps at the same time, right? Do you see any cars? How many cars are there? 0. There are 0 cars. Why is it a red line on Google Maps? Because there's 99 cell phones on the bridge. And Google Maps equates a cell phone as being a person, and a person is likely being in a car. And so if there are 99 cell phones on this tiny bridge, then what's happened? And what do you think Google Maps is now telling all drivers in the neighboring vicinity to do? Take a different route. Empty bridge. You can do a lot to really mess with the people in terms of routing. And with this, I am moving into a second think, pair, share. How do I do this network-wise? And you don't necessarily need to do it the way the bridge person was doing this with simulating traffic. But how do I use the technologies I have just described to go, oh, wait a minute, sorry, this is a look ahead. We're not talking about this yet. I'm going to present the technologies I'm about to describe. How do I use the stuff I'm about to talk about to make this happen? To just cause traffic to come to me, where I can man in the middle of it. Oh, and how does this attack differ if the attacker has a specific target as opposed to if they're a data aggregator and they couldn't care less and they just want a lot of data? All right, so for this, we're talking about BGP. This is called Border Network Protocol. We are still in this kind of weird space where we're halfway talking about security and a lot talking about networking still. Border Network Protocol is how we sort all this stuff out. So here we have the OSI network model on both sides. What's happening is traffic comes down across the model, it comes up the router, and at this point, the router does what I've kind of been showing on the screens, where it's switching the IP addresses in and out, right? So it's changing the IP addresses, it's maybe changing port numbers, because keep in mind, those ports I showed changing, those might be changing on every border router. And so, but what should the next hop look like? It has to adjust things for the next hop, but where should it go? How do I do routing to this network? Or think of it this way, which route should Alice's traffic take? Should it go up through British Telecom? Should it go down through Telenet in order to reach Bob's server? It obviously must go for Verizon because that's the ISP for Alice. And it must go through level 3 because that's the ISP for Bob's server. But the whole middle is debatable. And we want to minimize costs. Keep in mind, cost is defined by the companies. So what happens is that every border network router sends out advertisements across all of its large connection trunks. So keep in mind, these are big routers. These are not the kind you have in your house. And they don't actually have that many connections that they're working through at any given moment. Okay, now we're starting to get off the edge of my knowledge. I have not actually been a network engineer at a larger switch point, but they're working with a finite set. And they maintain a list of, from their position on the network, where can they reach? So what they have here is a set of IP address ranges. Now, if you remember back when I was lecturing about IP addresses, they are hierarchically built. They have a class A, class B, class C, and class D. It is normal for a singular entity to manage a range of networks of IP addresses. And so what they're saying is that if you want to get to IP address 10.0.0.0 through 10.0.0.255, then the next IP address I need to send it to is here. This is the weight associated with this, and this is what I think the path is going to be. These numbers here are autonomous system numbers. So that means I think that this will go through 65001, and then I suspect it's going to pass that to 65010, and then I suspect it will pass it to this next one. All right. It advertises this table out to all its neighbors. All of its neighbors then take their identical looking tables. They add their own weights to it. So they basically say, well, I just got this table in from my neighbor. Getting to my neighbor costs 100, so I'm going to add 100 to every weight on this table. I will now look and see whether or not for each address range, my new connected one has a smaller now weight than the one I already have on file. If it's smaller, then I'll update so that I go through the cheaper route. If it's bigger, then I won't update because I don't want to send it to the more expensive route. What you're looking at is effectively a ground-up greedy algorithm. Every network is just, AS is just talking to its neighbors and trying to figure out what the cheapest route is to its neighbors. If it updates any of these, it will send out a new announcement and say, I can now reach my neighbors at this weight. All right, BG propagation is what I was just describing. So when you look at this, what's happening is this router is sending out a set of weights. That router is sending out a set of weights. And again, every single one is. And then what happens is the traffic starts out, it hits Verizon. Verizon looks up its table. It says, is it cheaper for me to go towards the British Telecom direction, or is it cheaper to get to the Telena direction, given that the IP address I'm looking for is in the range over here for Bob? Or it's basically in the level 3 range. I have to get this traffic to level 3, and then level 3 has to sort it out. So, maybe it's cheaper to go to Teleka. Teleka comes down. It takes a lookup table. Teleka only has one connection, so it's like, this is easy. Forwards it. Level 3 pulls it up and goes, this is an IP I manage. I will go send it through my local system to Bob, because Bob is one of my direct customers.
Are these tables that are used internally something that is, let's say, secure, similar to how we're talking about how these certificate authorities?
There is no encryption on these tables.
What I mean by secure is that there's a list of trusted on the system. So
we do very little security in networking. We hope that for security more than we get it. So these are trusted in that they are maintained by the local AS. In theory, the server is, okay, so maybe I do understand the question.
Yeah.
The local server will try to protect these routes. First off, it's just desperately trying to not get attacked to start with. And it will not protect them at the level of keys, though, because it has to edit them every 2 seconds. And so if your primary thing is continuously editing and looking this up, it must be in working memory.
Right, but you're not able to, just as a consumer, follow the protocol and say, hey, I'm an AS, route through me.
Yes and no. So to become an AS, there's a global list of ASs. Okay. So you must put an application process to be an AS. That said, if, say, Jacobs decided their local network was going to become an AS, they can pretty much do it. Then you have peering agreements. So that AS, in order to create a connection to another system, must set up a peering agreement. And that requires paperwork, but this is dependent on every AS. So if the Waterloo Rogers decided that it was just wanted to give this to free, they could. There's no checks on that, really. I think that's the question you're asking. A lot of this is also trust-based. So the people who write the BGP protocols, I'm describing how the protocol works in general, but there's usually a custom rule set that is set up by every company, in which a company is like, I do not route through Russia if I could possibly avoid it, and they may code that in. That is a decision they're making. As I said, these weights are decided based on the company. So when they get this route in, they may go, okay, this is the route in. I'm going to add weights to everything I get from this route according to whatever my local economic situation is. All right, other questions? All right, now we hit Syria. Again, if anyone needs to leave the room. I picked this partially because they had a much better video than some of the other ones. And I'm hoping this is aged out enough that it's no longer triggering. I am sorry to say that I'm about to present to you is probably the same thing that happened in Iran recently. It's happened in Egypt several times and happens in a lot of places. Syria just turned off the internet. According to Edward Snowden, actually 2 years after this, Syria did not turn off the internet. The US government mucked up when it was trying to hack a router and turned off the internet. But at the time, in 2012, we thought that Syria had turned off the internet. Broadly, okay, I'm not going to get into global politics too much, but I will give a tiny piece because it's necessary to understand. There was a bunch of rebel groups in Syria at the time. The Syrian army was having lots of conflicts with them, and in the middle of this touchy situation, the internet simply drops out for 2 days. This causes an international ruckus because we don't really like this happening, and a huge whodunit question. So some of the videos that I have all came out of the whodunit question. They're trying to understand, the Syrian government is saying that the rebels shut off the internet. The rebels are saying that the Syrian government shut off the internet. 2 years later, Edward Snowden says the US government screwed up and shut off the internet. It's actually shockingly hard to figure this stuff out. So instead, we look at kind of what happens. Yeah, this is just them both complaining. But let's talk about what shutting off the internet actually looks like. So I'm going to show you a video, but if you've never seen BGP routes, this can be confusing. So we're going to go through a screenshot of the video quickly, and then I will show you the video. So you're looking at is the Syrian network. Every AS here is a number, as we saw on the prior image. That number is unique. Each of these dots on here are actually massive networks. So all of Facebook, for example, might be a singular number. These are big numbers. All the lines you are seeing here, let's see. Each colored line is the shortest path between a network and Syria. Syria, a country, is one AS. Big things.
My friend is one AS.
Well, it's an autonomous system. It's a whole network. I'm really trying to pound in just how large of an object we're looking at on the screen. Each colored line is a shortest path between, say, like here's 2497, and it routes along this route to Syria. Okay, so these are AS network routes. These are public. You can pull these. They are not secret at any time. That's Syria in the middle. Syria is connected to 3 ASs. So the only way to get traffic to Syria is via this AS, that AS, or the one right above it, that AS. There's no other way to get traffic to Syria. And paths shift all the time. So you'll see a lot of shifting. Most of it is because the network has been turned off, but this shifting is actually normal within BGP. Oh, okay, the video didn't go. So one of the things about the routing I'm talking about is there's lag time. So what happens at any given AS is always stating what it got basically from its neighbors. So what's happening here is that 3491 has lost connection to that central. And because it's lost connection, it started advertising to its neighbors. It's saying, I can't reach Syria anymore. That's causing everybody downstream from it to start trying to reroute through the network. But that propagation takes time. So this router up here, 1299, has now just probably figured out that it can't reach Syria. So before that, it was saying, oh yeah, no, I can totally still reach Syria. I can totally reach Syria. Everybody routes onto that. Now it's saying, oh, actually my connection has gone down. And so it picks the next route it can find. I guess 1299 is being very slow about it. 3356 is also being very slow about it. And so you're seeing kind of the slower to update ones are getting a lot of traffic suddenly being routed onto them because they're still advertising that route address. But as the routes propagate, 1299 is now going, actually, I can't reach Syria. And so you're starting to see these routes vanish off of the tables worldwide, and then the video ended with this being the last route. And then Syria becomes isolated because there is no longer a BGP route to Syria. All right, is this making a bit of sense? I like this. Okay, I know it's an awful conflict, but I like the video for explaining what's going on.
That's a great idea. Play that again.
Yeah. Okay, I may need to go back. There, okay. Three, 3, 5, 6 here. I think it's figured out that it may not be able to route.
So in the graphic, it starts off a bit one-sided. Is that actually?
It's because of the delay in the
or is it
route.
just the timing?
Yeah, because of the delay. What's happening is every single one of these things is trying to decide what's the shortest route to Syria. It's not saying is it down. It assumes nothing's down. And so what happens is when its current shortest route suddenly advertises a table that has no route to Syria or an expensive route to Syria, it will route onto a different path. And so mostly what you're seeing is an attempt to reroute. The internet is really desperately trying to find a route to Syria. If it had been the case that, I think it's down here, 3561, I think, directly had a route to Syria. If this one, for example, had kept its connection when the other ones didn't, and this is what happened in Egypt, you would have suddenly seen the entire internet routing down through 3561. I don't have a good video for Egypt.
Time for this process.
Not long. I want to say within an hour or so. Keep in mind, there was a lot of speculation. It was felt at the time that the rebels had, or that the Syrian government had sent people into both of the 2 network connection points that exist within Syria and had ordered the network to be shut down. So there was a delay between the 2 different points and when they come down. So in the...
That actually kind of explains.
There's 2 wires here, right?
Yeah.
Or kind of 3. I don't actually know what this third one is. But those 2 wires, those are physical places with big servers with a big wire plugged into the side of them. So the most efficient method to shut the internet down is honestly to take over that building and pull the power plug. And both groups said that the other group had done that. But coordinating this to an instant connection is not something that either group cares about, so it's quite likely that one of those boxes had the plug pulled before the other box, which causes a delay. And it's possible that these little kind of ones up in the top, they are not caring as much about the route to Syria because it's several hops for them. Because when, okay, so the first group to notice that there's a problem is going to be these direct connections. And when they send too much traffic where the traffic is not coming back, and okay, I don't want to get too deep into networking, but these connections have occasional pings across them, or at the very least, they're doing some level of liveness test. They're saying, okay, if I send traffic to this router, do I get anything back ever? And if I stop getting traffic back, maybe I send it a ping or something. If that doesn't work, I remove it from my routing table and then I look to my neighbors and I say, which of my neighbors can access it? And that becomes my new routing table. And it's continuously updating it because the default assumption is if a network connection goes down, it's probably a lightning storm, a backhoe that's decided to cut through the wire. All sorts of really random physical events happen on the internet all the time. 2 companies decide they hate each other. I mean, stuff happens. And so BGP is assuming that there exists a route. It always assumes there exists a route. And it will pick the route, even if it's the weirdest route possible, going across the entire globe, it will pick that route and try to route traffic there.
Did we change anything as a result of that to not necessarily assume on?
No, we never change anything like that.
Does that create a whole
Well, because it will do it. It's desperately trying.
Sure, but doesn't that end up, like, you can see everything clusters up to the whatever 1, 2?
Yeah, it finally ends up on that one, and that's just where the network engineer stopped recording the video.
Right.
The final state is basically just that it doesn't exist on routing tables. All the routing tables will state until otherwise noticed, unreachable.
But you can get there faster if you propagate it out that this is not available to anybody. Stop trying to reroute.
There's no difference between that. Because, okay, so I'm propagating my entire table. If my table says I can't reach it, it will just naturally create what you're describing. There's no reason to mess with it because it will work. And the other thing is, okay, accessibility is deeply cared about by network engineers. They really care about accessibility. They would rather have these computers thrash around for a little bit and desperately try to find any route possible than they would try to make it faster to get a route taken down. Also, keep in mind that a government may have done this. And if a government is doing this, what is a government going to do with a protocol that says this route, this thing is no longer reachable? That is unsecured statement. They're going to launch it to just take this stuff out. Okay, how are we doing? Okay. All right, I think we have run out of time for today, but I'm going to go through the last little bit of this, and I'll briefly explain the think, pair, share, and then we'll probably end at that point. So Facebook did this to themselves once. So this is another this was a really problematic case. This one was so stupid. One of their network engineers deleted their own IP addresses off of the Border Gateway Network protocol. And because it was their BGP own announcement, it propagated out. So basically they shut it off at their own location. That propagated out across the network in under an hour. And suddenly Facebook went down. So you get all these great news articles where they're saying things like, Facebook can't be down, can it? But it wasn't just the DNS servers. They started at the DNS servers, but that caused actually for the border gateway router's IP address to be removed from all the other records. So how do you reach something that's not on the border gateway router system? They had to literally, and I am not joking, they had to break down the door of their own server room because they could not access it. How would you normally access it? You type in an IP address, right? How does the IP address connect to anything? It follows the border gateway protocol route. And that means that no one at Facebook, even someone sitting within their own building, could not SSH into a server. And how do you control access on a server room at some place like Facebook? You have a network-connected access control device that checks back in with the server to make sure whoever's accessing it has not been removed as a Facebook employee recently, which means that the access control panel was also broken. This means they had to physically bash down the door of their own server room in order to get physical terminal access to the router to go and rebuild this whole thing from the ground up. This was hilarious. But I don't have a good picture of that one. The think, pair, share that was supposed to be sitting here is imagine an attacker wants to do a man-in-the-middle attack. How might the attacker use the way the traffic is routed to make an attack possible? The shortest answer is to simply advertise a short route. This has been done accidentally by several groups. It was famously a couple tiny countries once advertised zero-length routes, and then the whole internet came and smashed them to pieces because all the traffic started routing through them. There is nothing stopping, though, a large country, like let's pick on both the United States, Russia, and China, from suddenly advertising short routes. Now what happens? All the traffic goes through them. And it now becomes trivial to do a man-in-the-middle attack with that group. All right, I'm going to stop lecture here. Monday, we have a midterm. Don't forget to show up to the midterm. It is during our normal class time, but it is not our normal location. I have posted the location on Piazza. It is clearly marked as midterm. There also exists a midterm practice quiz that you are welcome to take. Obviously there's all the lecture quizzes as well you're welcome to take. All right, thank you so much. See you on Monday. I'm not talking.